today's topic, which is on the teaching of calculus. So a very good afternoon again to all of you. This is my name here, and I'm going to speak today on the teaching of calculus, and this is my lecture outline. We'll first look at a simple concept map for the topic of calculus, and then I'll talk a little bit about the syllabus that is related to what most of you will be hopefully doing, and that's in additional mathematics. So I'm addressing the teaching of calculus at the secondary level in this lecture. We'll also move on to talk a little bit about, in fact, talk a lot about differential calculus, and then a little bit about integral calculus, and then marry the two by fundamental theorem of calculus. And I wouldn't say very much about applications of calculus, and then I will summarize the lecture. Now, before we go on to talk about the actual teaching of calculus itself, maybe it's useful for us to refer to some of the publications on the teaching of calculus. In fact, a lot has been written about on the teaching of calculus, and I'm just giving you a very small sample of some of the readings that you may be interested in. So again, before we jump into the teaching of calculus, maybe we would like to ask ourselves this question. What kinds of mathematics or what skills should students have before they are ready to learn calculus? So maybe that's important because we need to at least make sure that the students have a certain set of skills or master a certain set of topics before they come into a calculus class. So I'll give you maybe about, not too much time, 30 seconds, to maybe talk to your neighbor and come up with one or two ideas. Yes, just... Algebra, okay, good. What else? Indices, okay, that is like part of algebra, yeah? Okay. Limits, okay. Would you agree that coordinate geometry might be important for a second? I'm talking in terms of from the perspective of a secondary school student. Would you agree that functions and graph, important to have all these basic concepts mastered before they enter a calculus classroom? How about trigonometry? Yeah. Algebra, yes, you might mention, and also you mentioned indices and so on. So I lump it together as algebra and say not just algebra, but in fact manipulation of algebraic expressions. Yeah. The idea of a tangent, and one of you mentioned the idea of a limit. In fact, the idea of a limit in at secondary level may not be that important or crucial yet. But perhaps at a higher level in the JC or maybe beyond that, perhaps it's important to have this idea of a limit because you have a direct application of this idea in the study of calculus. Now, the next question I will ask is that, okay, we know now what a student should need. Maybe these are the basic set of knowledge and skills that the student ought to have before we say that they are ready to study calculus or to learn calculus. But what about the teacher? What do you think the teacher should know before the teacher is ready to teach calculus? Anyone? The 6 points, okay. In addition to that, okay. In addition to what the students ought to have known, what about the teacher? Yes. What else do you think the teacher, yeah? Okay, my first point is plenty of calculus. Would you agree? Yeah? I mean, if you want to teach calculus, you should know calculus itself, right? Or, in fact, more than just what you ought to know to teach, yeah. Perhaps you also should know the formal definitions of things like derivative, integral, and so on, even though you may not really need it or use it in the classroom. As a teacher, I think it's important that you know the formal definitions. Perhaps also the idea of the fundamental theorem of calculus. Then perhaps applications of calculus. It's good as a teacher to be aware of how calculus can be used and applied in various other disciplines as well as in the real world. Yeah, yeah, I also think that some history of calculus will be useful. Very often, mathematics teachers are sort of, I wouldn't say accused or criticized, but singled out for not telling enough stories in the classroom, right? We are sort of portrayed as just going to a classroom, listing out formula, giving examples, and that's the end of the lesson. Maybe it's good to know some history in terms of calculus, and also perhaps to have an idea of the colorful characters involved in the discovery and development of calculus, so that you can tell some stories. And I will be telling you a story later in this lecture. Maybe some numerical methods for solving problems in calculus, although again this is not needed in the secondary level, nor in the junior college level. Yes, if you are doing H3, there's some numerical methods for differential equations, but in terms of secondary mathematics and additional mathematics, for calculus topic, you actually do not need numerical methods. But I think as a teacher, it's good for you to know a different set of methods of solution. It's probably also good to know some IT tools, because you may use these tools for your teaching, for your demonstration, and so on. Yeah. It's also perhaps good to have a good sense of knowledge in pedagogy or pedagogical content knowledge related to calculus, so that you are able to provide the kind of experiences that's necessary for the learner to not just know but also understand the concepts in calculus. And perhaps many more things, yeah, and so on. So that covers everything, yeah. So essentially you find that in order for you to be a competent and a good calculus teacher, there's a lot you can do in terms of preparing yourself for the teaching of calculus. So now we know how the student should prepare himself or herself, and we know how the teacher also, like you, should prepare yourself. Let's look at the topic itself in terms of a concept map. Yeah. If I were to ask you to draw a concept map, linking all those concepts and topics and so on that will lead to calculus, you can draw a different set of different pictures or different concept map as this one here, but this is one way of relating the different topics together. You probably would agree with me that functions in terms of the different kinds of functions, trigo functions and graphs of functions and so on is an important prerequisite. We have already said that before, yeah. So this will hopefully lead on to the ideas of limits if that is necessary, for us to move on to calculus. And under limits, you have ideas like Riemann sum and tangent to a curve, rate of change, and so on. Yeah. And eventually, these ideas will lead on to differential calculus and integral calculus, and also the fundamental theorem of calculus. And from there, then we can talk about the applications of differential calculus as well as the applications of integral calculus. And this whole thing forms at least what we know to be what is important within the topic of calculus. So these are the topics or subtopics that will link together that form something like a concept map. Now, this is not, of course, the answer or the model answer, but it is one way of representing the connections. Yeah. So let's now look at the syllabus. This is the latest new syllabus or extract from the syllabus of the additional mathematics 4038. There's an older one which will be phased out, I think, this year. So will be very relevant to you, because even if you go to your practicum next year, and if you have to teach additional mathematics, this will be the syllabus I believe that you'll be teaching. There are some changes, and I will not go through everything, but I just want to show you these are the topics that are in the additional math syllabus. It is good for you as a teacher to be aware, at least look through it, Okay, at least have an idea of what the topics are involved. Yeah. There are too many topics here to sort of to go through in a short lecture like this. So I will suggest that you run through these topics in your own time, pick up a additional maths textbook, and then maybe look through it and see whether in terms of the topic itself, calculus, whether the textbook has sufficient coverage for these topics and so on. I mean, that's a good exercise for you to familiarize yourself one more time. I know you have done this before, maybe many years ago. Perhaps it's a good idea to refresh and to familiarize yourself with the latest syllabus. It's also good to know what is not included in the new syllabus. Particularly these 3 points. Implicit differentiation, for example, has been taken out. Finding area of region between curve and oblique line and between two curves. This used to be in the syllabus and now it's taken out and so on. So my point is that it is important to be aware of what are the topics within calculus that a secondary school student ought to learn. Yeah. Okay, let's move on to the next section on differential calculus. I think the most basic and fundamental idea or concept in differential calculus is the idea of the derivative of a function. In fact, the word derivative here of a function, it just means a derived function. It's a function itself that is derived from another function. Okay? Those of you who are interested in investments and investing in stocks and options and so on would have heard of financial derivatives. So a financial derivative is not really something, but it's something which you derive from the basic stocks and so on. So in the same way, the derivative of a function is something that you derive from another function. So what are the ways of introducing this concept and so on? Again, I refer back to what David Toll mentioned in one of his papers. Now he said that the job and the duty of a mathematics educator or teacher is to provide a range of different experiences, okay, to develop the ideas of, let's say, calculus in a cognitive manner so that the learner can both know as well as understand. So I think in this case, if you want to talk about introducing a concept, it is good to be able to have a range of different ideas or different ways of introducing the same concept. Okay, so that if a student has difficulty understanding that concept from this angle, there's an alternative way for him to understand. So I think that is an important point. I think that is a good so-called philosophy to adhere to. So here I give you 3 ways that you may think about or choose or even develop yourself possible ways of introducing the same concept, the idea of a derivative. One is by definition. The other one is by description. And the last one by drawing. You see, I have intentionally chosen 3 words all starting with D, so it's easier to remember. So by definition, this is the definition. Right? So I will go through some examples. Perhaps a few examples just to show you how to use a definition, for example, to find the derivative of a function. Okay, this is my first example. And suppose I want to find the first derivative of f with respect to x. By definition, that's the limit as h tends to 0 of, let's say, f of x plus h, take f of x divided by h, right? Okay, so I'm going to just work through the whole thing. Now, I'm going to use this as my f of x, and whenever I see x, I replace it with x plus h. So I have something like x plus h squared plus twice of x plus h, take 1. Take away x squared plus 2x, take 1. And the whole expression is divided by h. Now you can go through the algebra and so on. That's why algebraic manipulation is one of the skills that we think that students ought to have. I'm not going to go through the whole thing, but we know that the x is going to cancel with the x square is going to cancel with that one, and then you have a 2xh. And you have a h square, and then plus 2x minus 2x, that goes, plus 2h, and then you have a negative 1 here and a positive 1 there, and that goes to 0. And so this is the expression that we have, and of course we can then divide numerator and denominator by h, and as h tends to 0, you are left with 2x plus 2. So that's how we can use the definition to find the first derivative of a function. This is not too hard. The next one is slightly harder, only slightly. In school, particularly in secondary school, we'll tell students that the first derivative of sine x is cos x. When your students ask why, you will say, don't ask. Just take it that it's a rule. I think it's okay to say that if you really know why, but the reason why you are telling the student not to ask is not because you do not know, but because they are not ready. I mean, that's fine. But if you say don't ask because you do not know, I think maybe that's not so nice. So if you have not come across the actual derivation for the first derivative, I'm not going to do it here. You might want to discuss it with your tutors, because we do not have time to do so many things, but it's a good idea to go and find out. Yeah? So this one, you either do it yourself or you discuss it somewhere else. I will discuss the next example here because this is a little bit more interesting. So suppose you are given function f of x equals to a to the x. A is some base that's constant bigger than 0. And you want to find the first derivative of f with respect to x. Again, if you use the definition, that's the limit as h tends to 0. I'm going to put the expression in straight away. So that will be a to the x plus h. That's my f of x plus h. Take away a to the x, that's f of x divided by h. And simplify a little bit by taking out the common factor of a to the h, a to the x. You have a to the h, take 1 over h. And in this case, of course, your a to the h is constant with respect to h, so we can take it out of the limit here this way. Okay, so we've reached this stage and we ask ourselves, what is this limit? So now we are in trouble because we either have to evaluate this limit in some way, and students at secondary level may not be quite ready to evaluate this limit. But if we don't do that, then we can't really have an expression for the first derivative of f with respect to x in this case. We can do this several ways. Let's experiment and see what happens. Now, if it turns out that for different values of a, this limit will be different. Okay, I say that again. For different values of a, this limit will turn out to be a different number. So suppose we experiment with different values. Okay. So suppose I take a to be 2, and it turns out that when a is 2 and let h goes towards 0, Okay, I can try both left hand and right hand, doesn't matter. It turns out that the limit tends towards a certain number, 0.693 in this case, yeah. And if I take A to be 2.5, the limit turns out to be another number, 0.9 something now. If I take A to be 3, it's 1 point something now. And 3.5, 1.252, and so on. So if it's not very interesting if we stop here, right? But perhaps it is good to ask a question. Yeah? It comes back to the special number which I asked you to list out at the beginning of the lecture. And one of the numbers, the first number you say that's special is 1. I agree with you, 1 is very special. So suppose we want to find out at what value of A will I get a limit which is equals to 1. Maybe that is interesting, yeah. So we can sort of analyze it this way. We have something like A to the h take 1 over h. If h is small enough and for a special value of A, or some value of A, I want this to be very close to 1 or going towards 1, yeah, if h is small enough. And it turns out that I can sort of write this down as A to the h equals to, say, 1 plus h. Yeah. And that means that I can write it down as A is, maybe I should say approximately, and A is approximately 1 plus h to the 1 over h. We can write it in another way. Instead of saying h, we can let h be 1 over n. Then I will have an expression that is of the form 1 plus 1 over n to the n. And if I take the limit as n tends to infinity, this would actually give me the number e. Okay? So in other words, e as in 2.718 and so on. In other words, we have a special case here. If f of x is equals to e to the x, then f prime x is equals to, this will be 1, so I will get e to the x. This is a special case. So you see that what I'm trying to say here is that there are different ways of motivating or stating the same thing. Now, if we are talking about teaching at the perhaps the secondary level, there's the first time that the students are encountering derivatives, differentiation, and so on. And in order to give them an idea of what is the derivative of e to the x, and by the way, that's included in the additional maths syllabus, you may want to just write this down as a rule, because you may not want to go through the whole thing. Or alternatively, you may want to go through this thing, but then not asking them to evaluate this limit, because they probably will not be at a stage where they are able to evaluate limits. So it all depends on how well prepared your students are. But on the other hand, when you suppose you're teaching the same thing at a JC level in H2 Maths, for example, you may want to try to use what I've just done, going through the same thing and having your students experiment with different values of A, and then finding that particular special value of A, which will give you this result. At an even higher level, let's say in the university, you may also do the same thing, but instead of experimenting, you may want to, because your students may have already learned how to evaluate limits, you may want your students to evaluate this limit. So you see, at different levels, for the same thing, you can provide different experiences to the student. The point is that you need to know at what level you're pitching, and whether it's appropriate or not, and whether your students are ready or prepared for that kind of treatment, right? So that's my point. So much for the first way of introducing the derivative. Another way of introducing or talking about derivative is to describe a derivative, a gradient or tangent graph of a function at a point. Or you can describe it as a rate of change. I've checked some textbooks, and this is how some textbook writers describe the idea or put forward the idea of derivative. They describe it as rate of change, they describe it as gradient of tangent graph at a point. But this, again, in words, it may not be easy to see or understand. So perhaps a third way is by actually drawing the graph. You talk about a gradient of a tangent graph at a point and so on. Perhaps it's good to illustrate that with an example. So I'm going to use this same example which I used just now. Suppose you have a function fx equals to x squared plus 2x minus 1. This is how the graph looks like. Suppose I want to know at this point what is the gradient of the tangent. Now, what do I understand by it? Let me just focus on this point first, right? And suppose I want to zoom in closer and closer to this point. Obviously, I can't really do it in any other way except to use some kind of technology. Like this, for example, using Graphmatica, and I trust everybody in this room knows how to use Graphmatica, right? Yeah. So this is the point that I'm talking about here. Okay, and suppose I want to get very close to it. Let's see what happens. Okay. This is what it looks like now. Let me zoom in some more. Okay. Perhaps I zoom in one more time. Yeah. I don't know about you, but my curve becomes a straight line as far as this part is concerned. This part of the curve, as I get very close, and I zoom in and zoom in and zoom in and so on, it looks like a straight line to me. In fact, what kind of straight line does it look like? Let me see. Let me just draw this other line. I've just drawn a line on the same graph, y equals to 4x minus 2. Can you see the line? Can you see the curve of the line? You can't see this. It looks like I have not done anything. Maybe they are a bit too close together. Let me zoom out now. Yeah. I'm not sure if I'm zooming out. Am I zooming out? Oops. Oh yeah, I'm zooming out. Oh, now you can see the line and the graph, right? This was the line I drew, the straight line I mean, and this was the original graph. Okay, so you can see that when we talk about the derivative, what I have drawn this line here, in fact, is the equation of the straight line that is actually the tangent line to the graph at this point. All right? That is y equals to 4x minus 2. And you find that if I zoom in very close to that point, in fact, we're not talking about just the derivative giving us the gradient of the tangent to the curve. It is the gradient of the curve at that point itself. And this was the point that David Toll mentioned when he first used technology. He was the first few people to use technology to illustrate this idea of gradient of tangent of a curve at a point using a graphing tool. So we might want to use something like this, some kind of technological tool to illustrate the idea of derivative. Now, more on differential calculus, when we talk about the derivative and so on, we are also talking about a function which is differentiable at different points and so on. It's also good to know when are the situations when a function is not differentiable. Again, I give you three scenarios where function is not differentiable at a discontinuity at a point where there's a vertical tangent and at a kink. A kink here means something like a sharp corner. Okay, to describe it in a very loose sense, that is a sharp corner. Now I'm going to show you a couple of examples, three examples, and in each of these examples, the function is not differentiable at x equals to 0. So this is the first one. If you have fx equals to 1 over x squared, for example, at x equals to 0, all right, there's a discontinuity and this function is not differentiable at x equals to 0. Another example is, for example, we have f of x equals to cube root of x, and at x equals to 0, you have a vertical tangent, and by definition, the limit at that point for the derivative, if you use the so-called definition of the first derivative, you will have a limit to evaluate, and that limit at x equals to 0 does not exist. So it's not differentiable. And this is the third situation. Let's say we have f of x equals to mod x, or absolute value of x. You find that at this point here, at 0, 0 here, there is a corner. I mean, to put it in very simple terms, there's a kink. And at that corner, the function is not differentiable. The word kink is to illustrate a situation like this on a graph. So if you have many corners, such corners in a graph and so on, you might say that the function is very kinky. Yeah. Let's move on to integral calculus. Okay. Again, I think it's important to sort of know how to introduce integration, what is integration, and so on, and what are the ways of introducing this concept. And I find that in many of the secondary school textbooks, they usually introduce it as anti-differentiation, or the reverse process of differentiation. But that may not be the only way to introduce a concept. Yeah? And perhaps we can talk in terms at higher level as the limit of a Riemann sum and area under a curve and so on. So again, due to time constraint, I'm not going to talk about so many things, but just focus on the idea of approximations to areas as a way to motivate integral calculus. And tell you this story about Archimedes trying to find an approximation. Actually, he was trying to find an approximation to pi. And using what we call the method of adsorption. In this case, the method of adsorption doesn't mean that he applied the method until he got so tired. No, it means that he will increase the value of n. In this case, n is the number of sides of a regular polygon as inscribed by a unit circle as shown here. And I'm not going to go through all the mathematics. I think you can figure it out yourself that theta in this case is pi over n, where n is the number of sides of this regular polygon. And of course, theta is in radians. And this n-sided regular polygon will have an area of n over 2 sine 2 pi over n. That's one little box in your handout that you fill in, but I think it's good for you to go through the exercise to see if you can derive it. Hopefully some of you have already done it before coming to this lecture. And of course, if you want to use this idea to find the area of the unit circle, circle, that means the radius is 1, you will let n tend to infinity. Right? That means you have more and more sides of the polygon, and as you increase the number of sides of the polygon, well, you get to a situation where the polygon is almost looking like the circle. All right? I promised to tell you a story. So I'm going to tell you a story about Archimedes. No, it's not about him and Eureka. And it's another story. That's why I say there are actually many colorful characters in mathematics. Yeah. And it's good to read up on, read a little bit about these characters. Now, Archimedes was a very intelligent, as you would expect, very intelligent man. And because he's so good at solving problems for his people at that time, he became quite famous, quite well known. And at a time when his city, Syracuse, was being invaded by the Romans, the Roman leader actually knew that there's this man called Archimedes and ordered the soldiers, you can kill anybody. He told the soldiers, you can kill anybody, but don't kill Archimedes. Because I think they realized that he was still useful to them. Yeah. So there was this Roman soldier who went to Archimedes' house and then asked him, who are you? I have to make sure, before you. So ask Archimedes, who are you? What's your name? But at that point, Archimedes was very engrossed in solving a problem, you see. And of course, they didn't have tablet PC and all that at that time. They have tablets, but stone, not tablet PC. And he was drawing his circles on the sand, in front of his house, was drawing this in the yard of his house, and was drawing his circles and so on. This soldier came and interrupted him and asked him, who are you? So, of course, he got very irritated and said, hey, don't disturb my circles, So, of course, he did not give the soldier his name, so the soldier killed him. That's how he died. It's true. Or at least that was what was recorded, yeah. So anyway, that's one story, and that's about Archimedes. And he was probably the first person to put forth this idea of method of exhaustion, and this gives rise to what we now know as limits, and the idea of using it as a way of finding the area of plane figures. Yeah. So we can also introduce integral, parallel to what I've just described as area under a curve. And again, I'm not going to use do it by hand, but use a tool like this. For instance, if I were to use Graphmatica, I can actually use this to find the area under this curve, let's say from x equals to 0 to x equals to 5, about there. So 0 to 5, yeah? And maybe if I want the right-hand sum, maybe not 10 rectangles perhaps, and I get something like this, yeah. So, and I got answer something like 10.4616. If I want higher accuracy, obviously I can choose more rectangles, and I get something like 10.6922 and so on. And you can see that I'm using integration, in this case numerical integration, to find the area under this curve. And that's also one of the ways to, in some sense, motivate the idea of integral as area under a curve. Yeah, so we have talked about differentiation and the derivative, and it was developed to solve a certain set of problems, mainly rates of change or tangent to a curve and so on. And we have talked about another problem, which is to find areas and so on. And it turns out that these two apparently, seemingly separate problems are related, and they're related by the fundamental theorem of calculus part 1, part 2. I'm not going to go through the details of this, but I just want to mention that this theorem basically tells us that there is a relationship between integrals and the derivative of a function. And that is the beauty of mathematics. This theorem, in fact, is a very powerful statement. Let me again go back to what we did right at the beginning of the lecture, when I asked you to give me a few numbers, 5 numbers, and we put all the 5 numbers together, and we could find an equation that relate all these apparently unrelated numbers. So we have e to the I pi plus 1 equals to 0. Now that is the beauty of mathematics. In this case, we have two ideas or two concepts. At that point in time when they were discovering or developing these two concepts or ideas, nobody knew or thought that they would be related, and finally there was this theorem that connects the two, that connects integration and differentiation. And in mathematics, very often we find such things happening, and you begin to wonder, something like calculus, for instance. Is it really an invention? We know that Leibniz and Newton had independently developed this idea. Of course, during that time, they fought over who is the original so-called inventor. All right? But is it really an invention, or is it really something that is already there but waiting to be discovered? So again, this is a very philosophical kind of question that I will leave it to you to decide whether you want to discuss it in your tutorials or leave it to your tutors to decide. But that is one idea about what we can do with our calculus and so on in terms of discussing it at a higher level. Applications. That's the next section. I think we all know that calculus can be a very very good topic where you can, to use as an example where you can apply it to different disciplines, whether it's in the sciences, in economics, in social sciences, in engineering, and so on. There are many areas where you can use calculus. So I will not go through all that, but then just bear in mind that these are the topics which are probably, it would probably be good that if you are not familiar or you have forgotten some of these problems that arise in the applications of calculus to go back and revise and refresh. Like I said, I don't want to say too much about this, but later on I promise you a performance on this application of calculus in terms of velocity, acceleration, and so on. So let me quickly conclude. There are some pedagogical issues that I think we ought to think about, and I have 4 points here. Okay? The first point is computations versus concepts. What do I mean by that? Now, we can teach calculus in a very computational, mechanical way. That means you just tell your students, this is a formula. Don't ask why. You don't have to understand why, but you just use this formula, use this, and you just go through, practice 2,000 problems on this, and you'll be good, which may be true, yeah. And or alternatively, you can say, okay, this is a concept. You can describe the whole idea of what is a derivative and so on, and then giving very little practice. I mean, whichever way it is, I think extremes are not so good. So I think a good way is to balance the teaching of calculus with understanding of concepts as well as the need for some kind of drill and practice. Computation, yeah. Instrumental understanding versus relational understanding. So if you only teach procedure, you are only giving one way of understanding, which is instrumental to the student. Student may be able to perform some differentiation or some integration and so on because the student has memorized the steps. But that is only instrumental understanding, may not be able to relate to the actual concepts and so on. Perhaps it's also important to balance between these two extremes. And this is, of course, put forward by Richard Scamp. So I'm trying to relate to whatever you have done in theory of learning, learning theory. Okay, flavor versus rigor. I think just now, earlier on, I went through the whole process of solving or finding the first derivative of certain functions. I used 2 examples from first principles. That is to demonstrate to you the rigor that can be involved in even finding first derivative of a function. But do you really want to go through that in your secondary school classroom? Maybe not. But do you just say that, okay, we don't care about the rigor and we just memorize the formula? Maybe not. So Flavor, by giving a flavor, that means that sometimes you may not want to go through the whole rigorous process of from first principle solving certain things, but you may want to talk about how it can be done without actually getting your students to do it. That's what we mean by flavor. Give a flavor. Or you may show examples, but then you can always tell your students that at this point in time, maybe they're not ready for the full process of going through the rigor. So my point is that at different stages of their development and understanding, the student may or may not be ready for a certain level of rigor. And as a teacher, you need to be able to assess and then judge. So again, rigor by itself sometimes may not be appropriate. That means you do all the very rigorous mathematics without, caring whether your student can understand. That may not be the best way. But then again, without the rigor, it also may not be very good. So again, a balance between giving rigor and giving flavor. Finally, applications versus appreciation. I think, like I said before, calculus is one subject one topic within mathematics that you find many applications in, and also in other disciplines and so on. But do we want to teach calculus because of that? Like, we can just apply anywhere and so on, rather than teaching it because it's a beautiful subject by itself. That's why in this lecture, I also show you certain ideas and maybe some of the things I've talked about is to help you raise the level of appreciation for the topic as well. Okay, so these are some of the pedagogical issues that you may want to think about yourself, and whether you subscribe to one or the other and so on. At the end of the day, as a teacher, you should have your own conviction about what is most appropriate for your own student. Okay, thank you. That's the end.